So after we have seen how MapReduce works, main concepts and some examples, let's see now how we can use MapReduce to execute SQL queries. For this, let's take one relation R with attributes A, B, and so on, and we assume that this relation is stored in a file, one tuple per line, and this is like lying in our distributed file system, and we can now execute some MapReduce jobs. So how would we set up map and reduce in order to compute, for instance, this very standard SQL query? So here we have a select B, so the B column. We also call this, of course, a projection. Like in relational algebra, we would write like this. From this relation R, where a predicate holds that is executed on this attribute B. Here, this is what we call selection, and this is how we express this in relational algebra. So how can we do this? So basically, we have this huge file, which is chunked up again, and it's happening, or it's placed in the distributed file system. And now we want to get those tuples, for instance, this one here and this one here, that fulfill the predicate. And from this tuple, we only want to have the B attribute. Now that's a very simple query. There's no join involved and no aggregation. How would we execute this? Now, this is basically exactly the same as we have seen already for the grep example, like this Unix tool implemented in MapReduce. So we need only a map function. We don't need any reduce function. And this map function takes as input a tuple, checks if the predicate is true, and then emits only the B attribute from the tuple. Right? Now this is like the simple example here, but we can make it quickly more complicated by saying we want to select distinct. Because if you're selecting distinct, you cannot just output the B values, but you have to do duplicate elimination. For duplicate elimination, you need to know global knowledge, and this cannot be done only at the map side. In this case, you also need to have a reducer working, and you can think how you would do that. Okay, a little bit more complicated query involving group by and having. Here we have like a salaries table, and the salaries table contains the department and the salary of an employee and the name and so on. What we're interested in is getting the department name or ID, doesn't really matter here, and the average salary for everyone working in this department. And we want to have this only for those departments that have an average salary larger than 50,000. So how can we do this in MapReduce? So look at this query closely. We have here again, like before, select and some projections, but here now we have an aggregation, which is also expressed by this group by. So we want to know the average salary per department, right? And when I'm saying per department, it means that we have to group by department, obviously. So how can we group by department? We have to bring all the tuples in one place that have the same department. And how do we do this in MapReduce? Well, the output of the map, so if we have our map function here, that gets some ID, we can ignore that now, and here we have the tuple T of this salaries table, and there's like the emit function call, and here the first one is the key we're giving, and according to the key, the tuples are grouped to the reducers. And what do we do here now? Well, we have to take t.department as the key, because then MapReduce is able to forward all the tuples to the individual reducers according to the department ID or name. Right? Let's say we have IDs here, so then we would, for instance, have department or some employee information. The person is working in department 10, and then this tuple will be sent here to this partition for this reducer, and there's another person working in department 10, and of course we know how MapReduce works, and that means all the 10 or all people working in the department 10, the tuples are forwarded to the same reducer. And tuple or the department with ID 20, they might go here, and with 40 they can also go here, right? We know that this can happen or this will happen, but when we look at the reduce function call, this does not create any problem, right? Okay, so what information do we have to send here as the value of our emit? So what do we do here? We're computing the average salary. So of course we need to know the salary. So we have to send t dot salary to the reducer. And if we require more information, then we have to send more tuple information. The full tuple t is not needed here because we only need a subset. So this is of course now what the map is doing. And then at the reduce side, when you're looking at the reduce code, there we have the key as the first parameter. Here in this case, the key, we can already say this is the department ID. And here we have now an array of all the salaries. And then we take this array and we compute the average. This will be the average for this department. And if this average is larger than 50,000, then we emit the department ID and this average. Otherwise not. And this is how you're implementing this query in MapReduce. Right? And here we have it again written, what I just explained. So these queries, well, the second one was a bit more complicated because it involved aggregation, but still it was kind of simple since it did not involve any joins. It was only on one relation with salaries information. So now we have here two relations, R and S. And you see here we have R with A and B attributes, and here we have BC attributes. Now this, of course, looks already like we want to join it, and yes, we want to join it. And here we are writing the join query, select everything from R and S where this join predicate holds. Of course, we could also write it differently. We can also write the natural join, because here the B attribute is common for both, and we can also use the expression join on this predicate, but here this is the same. Anyway, the database system would solve it like this. So this is a typical join query, an equi-join query, because we're testing for equality here. And note this already now, because I'm saying this here, this is like an, of course, equi-join, and there could be also other join criteria, like for instance this join, or we have more complicated ones like r.b minus s.b, absolute value is smaller than, let's say, 0.7, something like this. So we can have arbitrary different or difficult or complicated, complex expressions here. But in this case, we talk about equi-joins, and that's important now because the algorithms will be designed for equi-joins, and we will discuss also algorithms that can handle different kind of joins. But let's start for the simple case of equi-joins. So how do we do this in MapReduce? Here already we have the hint given. The join partners, so the tuples from the R relation and the S relation, that will be in the join results, they have to end up at the same node in the system, the same compute node, in order that we can check or we can match them, right? And how do we achieve this in MapReduce? So we have, let's say, we have a tuple from R. Let's say we have, let's work with integers only. So we have 5 for the A value and 8 for the B value. This is like in relation R. And we have one from S, which is, let's say, I don't know, 8 and 2, something like this. So how can we make sure that these two are meeting each other in MapReduce? We cannot assume that by luck they are in the same machine where the map phase is running. So here we have to make sure that they are meeting at the reducers. How do we forward information to the reducers in a deterministic and controlled way? Well, for this we have to define in the emit of the map what is the key, because the key controls how data is grouped or partitioned to the reducers. So now which values do we take in order to forward or group the tuples? Well, the B column has to be the same, so they have to match. So now what do we do now? We are emitting the R tuples based on the B value here, and the S tuples also based on the B values here. So you would write tuple.b in this case. And then we have to, of course, also send the tuple because we want to have all information. So that's the rough idea. It's not fully done yet. There's one little mistake we are doing if you don't pay attention, but you can think of that this is like kind of the idea, right? So it's always about what I said earlier. It's always about looking how you can get the data to the reducers in a correct way, and then you have to do some aggregation perhaps. If your query involves aggregation, some counting and so on. But first of all, the first task is always to see how do you get the required information to the reducers. So here's an example of a join, but I guess you all should know it by now, how a join looks like. We have joint attributes, or we have attributes which are different named, but then we have to specify the predicate. But anyway, this is like very basic knowledge on information systems and databases. So the first join, this was what I described already, is called reduce side join, because the join is done at the reduce side. So if you have these two relations again, the map has to take care that the tuples are correctly forwarded to the reducers. And as I mentioned already, we are doing this by taking the B value of the tuple T. So the map function would get some ID, we don't really care now, and the tuple T, we don't know now, we don't care from which relation the tuple T is, and then we emitting T.B as the key for the information we are forwarding to the reducers. And additionally, we have to also include the information where the tuple is from, because we do not want to join at the reducers tuple from S with tuple from S and tuples from R with tuples from R. We want to join tuples from R with S, right? So, and then the reducer receives these tuples and makes sure that we are not joining the relation itself. And by the way that this mapreduce works, we have already the guarantee that the B values are the same, because the reduce function call is executed for one certain value of B. Let's say we can call that, I don't know, B value, right? And here is like a set of tuples, tuple 1, tuple 2, tuple 3, and so on. And now we have to join them. We are guaranteed that all of them have the same B value. And now it can happen that, for instance, this one here is from R, and this from here is from S. So we can join them right away and emit them. We don't have to check the predicate again. But of course, if we have here T3, which is also from R, then we cannot join, or we should not join T1 with T3, right? So we have to take care. This is not yet checked, but the join predicate is checked. This is guaranteed by the way MapReduce is organizing the data at the reducers.